So,
all right. I will begin with a word of prayer. So, Heavenly Father, we thank you for this day. Thank you for the weekend. And just thank you for your many blessings. Help us to glorify you when we do this day, Lord, and just to understand a little bit more about capacitance, Lord. In my prayer, Lord Jesus. Amen. So, I didn't think this class had much potential, you know, until test one. But then after test one, I feel like we've had potential. So, just saying. Although, we're almost done with potential. So, let's see here. So, potential. This marker has no potential. Good.
right back.
So potential we have defined to be essentially the function that if we calculate the gradient of the voltage function, we get the electric field, right? This is the potential. And I would just remind you before that we discussed previously that the electric field has to satisfy what's called Gauss's law, right? And in differential form, it looks like this, right? Where the divergence of the electric field has to be equal to the charge density divided by epsilon naught. This is Gauss's law in free space, at least, right? So what does this say about the potential? Like, what differential equation does the potential have to solve? Well, if you plug in the definition for voltage into this equation right here, you get the divergence of minus the gradient of the voltage is equal to rho over epsilon naught. And then traditionally, you rewrite this as nabla squared times the voltage equals to minus rho over epsilon naught. And this right here is known as Poisson's equation. In the case that the charge density is equal to 0, you get nabla squared and the voltage is equal to 0. This character right here is known as Laplace's equation. So Laplace's equation is Poisson's equation in the absence of charge. Now, what does that actually look like? When you work it out in coordinates, the Laplacian, this nabla squared, is a differential operator. And it looks like, I'll write it down here. It looks like this. Nabla squared is partial x squared plus partial y squared. And if we're in 3D, and I guess we are, this is the Laplace operator. And so there. Now we're all awake. So there you go. I mean, this is pretty much your job in this class. As far as voltage goes, is you're just trying to solve Laplace's equation, right? Subject to a particular geometry and subject to particular boundary conditions, like you've got a certain amount of charge on the boundary and certain voltages are given. The good news is that mathematical physics proves through things beyond this course that the solution to Laplace's equation is unique. If I specify voltages on the boundary and if I specify a particular distribution of charge, once those are given, there is a unique voltage function which will solve all that, all right? And we found those voltage functions for a variety of different cases. You know, I guess, anyway, that's pretty much all I have to say. We've talked about how to find the voltage. So just to recap, we started with the Coulomb potential. We saw we could add that to get a couple charges. We saw that if we want to, we could deal with like the voltage for a line segment by integration, right? Or a disk by integration of a ring. And then more often than not, though, we have used sort of more sneaky symmetry-based arguments to find the more interesting voltage functions, right? Like the voltage for the Coulomb field or the voltage for the charged sphere, all these things, the uniformly charged cylinder, the spherical shell, all of these we have basically taken the tact of finding the electric field from Gauss's law and then basically integrating back to get the voltage and slapping a minus on, right? That's what we actually did. If you take a step back and look at what we did, that's pretty much a summary of everything we've done with voltage, which is again potential. And potential is, to be clear, potential energy per unit charge. All right. So that brings us to our next topic, which is capacitance. So here we go. What is capacitance? So capacitance is an important property of a particular, geometric assembly, I guess you could say. You have to have two conductors, right? You have to have two conductors, and then you've got some geometry that is connecting them. Perhaps there's some material between the conductors, whatever. But then the question is, if you put a charge of Q on the one conductor and a charge of minus Q on the other conductor, well then, if you take the ratio of that charge to the voltage, we define that to be capacitance. So, definition, the capacitance is equal to the charge divided by the voltage. Now, I will make that a little bit more precise with examples, okay? So I gave you kind of a vague paragraph about what was meant by that. And so, like, the fundamental example, of course, is the parallel plate capacitor. So, example 1, if we have plate here, right? And then I have another plate down here, parallel. All right, so I think about, putting a charge Q up here and a charge minus Q. Now these are conducting plates, right? Two conducting plates, so this is, metal, and this is metal, right? These are conductors. Then what's the direction of the electric field between these two? If I was to draw those, how does it go? Electric field lines come out of the charge and they go into the negative charge, right? So the electric field lines should look something kind of sort of like this, right? Now, I mean, truth be told, and maybe you've done some of this in lab. I haven't had a chance to check your lab schedule or anything, but last week, all right, woohoo! So you should see that they do bend around like that over there, right? And if you could somehow track it, they do all kinds of wonky stuff like this out here, But I really don't want to talk about that, so why am I writing it? So ignoring these, which are edge effects, all right? Ignoring edge effects, which I'm trying to do, but failing. All right, so there. I have erased all of the edge effects. Woohoo! In other words, think about the limit that these plates are actually really close together. So what happens out here is really, irrelevant for the most part. So if this is the situation, right? And then we say we've got voltage A down here. So we'd like to start talking about terminals. So this is like terminal A, and this is terminal B. So I could talk about the voltage at B, and I can talk about the voltage at A, all right? And that's relative to some specification of like ground. So when we think about circuits, we start talking about, a place where voltage is defined to be 0. So when I talk about VA and VB, I'm talking about voltage relative to some common reference point. That becomes important if you're actually measuring it in a laboratory, right? Like you have to connect a voltmeter relative to a common 0. Okay, anyway. So I have voltage A, I've got voltage B. How is the voltage A and voltage B related to the electric field here, and how is that related to the charge? So, well, we know. If these are plates with area A, then sigma is, let's say, Q over A, right? That's the charge per unit area. And what's the story? What's the electric field here? in my picture. And for the sake of specificity, let me call this distance here, this distance y, right? So I don't really need that for the electric field except to slap a y hat on it, right? It's going to be a negative something y hat, right? Fill in the blank for me. What should I put there? I've got the electric field from the charge of sigma over 2 epsilon naught up here going down, right? But I've also got the charge of the electric field of sigma over 2 epsilon naught from the charge down here, right? So those superpose, and they give me a half plus a half, which is 1. So lo and behold, we've got ourselves sigma over epsilon naught. Now I'm assuming for the sake of specificity that at the moment we've got an air gap. Air gap for the time being. We'll do better as we go on today, but for now, air. So then what? So what's the voltage then? If that's the electric field, we can write down the formula of the voltage, apparently. It should be what? It should be, well, sigma y over epsilon naught, right? Plus VA, whatever the voltage is at A. See, because when I put y equals to 0, I should get V equals to VA, right? And does this do that? Well, if I put in y equal to 0, I get V equal to VA. And so, great. Let's see here. So what, I guess I also need to know the characteristic distance between these plates. And I think we usually use a D for that. Yeah, D is the usual letter. So suppose the whole distance between the plates is D. All right. So let's see here. So if we were to do VB minus VA, what would we have? We'd have, sigma D over epsilon naught minus, minus VA. Okay. Oh, my bad. Plus VA, right? Minus, 0 plus VA, right? So minus VA. In other words, VB minus VA should be what? The VAs be canceling, and you got yourself a sigma D over epsilon naught. But what was sigma? We have it right up of Q over A, right? So we've actually got Q D over A epsilon naught. And so here, I told you I was going to have to explain what I meant by the definition as we went on here. And so here's my first point of order. When we say Q over V, what are we talking about? What voltage are we talking about? We're talking actually about the difference in voltage between the two conductors that define the capacitor, right? So we're talking about the difference in voltage. So it might be better in some sense to write this as, Q over the change in the voltage. That might even be a better definition. But people usually do say Q over V with the understanding that V is the difference in voltage between the plates, all right? And I will also do that, as it is our custom. So anyway, what formula did we just derive? We have found that if I say V is equal to VB minus VA, right? Then we've got what? We've got V is equal to QD over A epsilon naught. So therefore what? Q over V is what? Looks like I've got A epsilon naught over D, right? For this example, that's the ratio of the charge to the change in voltage between the plates, right? And as such, we have found the capacitance for a parallel plate capacitor is simply given by the area times epsilon naught divided by D. And again, that assumes that there's an air gap between them. Does this make sense? I mean,
is that like right there a law that'll take place no matter what? There's 2 points.
as long as we're talking about a parallel plate capacitor, so this assumes some things. Like one of the things it assumes is that the distance between the plates and the area of the plates is such that the distance is relatively small compared to the area of the plates in some sense. Like this would fail to be true if edge effects were big. Yeah, if the edge effects were dominant, then this becomes less true, but this is still pretty much true even if you have a plane that's like curled up in a like in a roll, like actual. Well, I mean, what I'm trying to say is, suppose you took a plane like this, if you could, well, and it's kind of like one of those cookies, right, with the cream in between. Like, imagine if you could take that cookie and somehow like roll it up into just roll it up. It would still pretty much satisfy this relation, as far as I know. I mean, there's got to be some correction to it, but that would be a good approximation for that anyway. And of course, that is actually how capacitors are often made, right? Is you take two materials, you wedge them together, and then you roll it up, because it's a lot easier to get a really, really large surface area by rolling something into a small space as opposed to, actually just having a large parallel plate. If you look at capacitors, they're typically like in a little can, right? What's inside that can is probably something like a roll, I think. I haven't really opened any myself. I'm just speculating, but you guys look into it. If I'm wrong, let me know. But not right now. I know you have phones, but Anyway, so first of all, parallel plate capacitor. How else could we form a capacitor? Well, let's see here. Oh, I have a comment, which is important. More of a remark, but so remark. Epsilon naught is equal to 8.85 times 10 to the minus 12th, 10 to the minus 12th farads per meter. So F is for farad. Farad is the unit of capacitance, all right? Farad is the unit of capacitance. If you could find a capacitor that has a farad of capacitance, that's a huge capacitor. Typical values are more like microfarads or something like that. Let's see here. So for example 2, just to put some numbers in here, for the sake of specificity, if I had an area of 0.001 square meter, and if I had a distance of 1 millimeter, then my capacitance would be A epsilon naught over D, right? Which is what? Like my A is 10 to the minus 3. Division by 10 to the minus 3 is what? Oh, it's just what? Duh. It's just 1 times epsilon naught. So apparently this would be a 8.85 times 10 to the minus 12th farad capacitor. I got to be careful with the units here. This is, what are the, let me be more careful. Let me put the units in. I do expect you guys to put units sometimes down, so like I probably should do it too, right? Uh-oh, I broke them. So this is meters squared, right? And this is meter. And the units for epsilon naught are farad per meter. So you see what happens? The meters, you get meters, meters, meters squared upstairs, meters squared, so they'd be canceling. And you're just left with F for farad. So there you go. Now, I should mention there's a special, I was trying to talk about some multipliers in here. So this is 8.85 picofarads. P for pico. A pico is 10 to the minus 12th. That is pretty puny, right? So do capacitors are elements that we design for circuits that have a specific known capacitance. But you should understand that anytime you bring two pieces of metal in conjunction and you put charge on them, there is a capacitance. Like, it's unavoidable. And this is a problem for computers, right? Because you have wires that are getting closer and closer and closer and closer together, and whether you like it or not, as they get close together, the distance between them gets small and the capacitance gets big, which could be an unintended consequence of it getting smaller, right? So this is something you have to deal with in building small things, is things have capacitance whether you like it or not, and you have to design for this. Yeah.
What's the practical result of capacitance? Does it heat up the wires, or?
Well, capacitance in a nutshell, it resists a, let's see here. Goodness, that's a good question. Heat up the wire? I don't know about that. I mean, it's a way of storing energy in an electric field. Like, ultimately, what's happening is as you add charge to the plates, you're storing energy in this electric field. And basically what happens is once the plates are fully charged, you're no longer going to be able to keep passing current through. So, like, long term, they act like open circuits. Short term, when they're completely uncharged, when you just add voltage to it, they just suck charge up. They're like a short circuit in the very short term, but they're like an open circuit in the very long term. I can tell you that much.
You can hold charge for a long time, correct?
Oh yeah, in some sense they behave like a battery. So, right, they can hold charge for a very long time. Yep, this is true. So it's important when you open up an electronic device, if you want to be careful, beware of the capacitors. They could be charged even if it's off, if it's not been designed in such a way to drain off the charge, and you could hurt yourself. I had an instructor in community college who burnt like an airsoft sized chunk of skin out of his palm, like just accidentally got zapped by a capacitor. They're bad. Anyway, they can be bad. Moving on here. So example 3, we could talk about a cylindrical capacitor. All right, so you could have, I need bigger. We could have a cylindrical capacitor. So here I have a pair of charged cylinders with at the moment, an air gap between them. Let's see here. So let's see. I said like radius R1 for the inner one, and radius R2 for the outer radius. All right. Anyway, so there is, I'm trying to illustrate here, is there is a gap between these metal cylinders. So if I drew it more like this, it'd be kind of easier to understand, I guess. So R1, R2, I'm saying you've got a metal conductor on the inside, you got a metal conductor on the outside. You got me? So metal, and this also metal. And we have worked this out before. I won't go back through it at the moment, but we've worked out that if I was to say, the voltage here is VB, the voltage here is VA, we derived it, and we found that we could calculate VB minus VA is equal to, the voltage at R1 minus the voltage at R2, apparently. Just a second, did I label them the same way? Voltage at R1. Oh, let me hold on. B, A. I need to be consistent in my labeling. So I made B the inside one and A the outside one in my picture, so let me stick with that. So VB minus VA is V at radius 1 minus the voltage at radius 2. The formula we worked out for that was, and to be clear, it's same deal as the last one, right? I'm imagining that there's a charge Q on the inside and minus Q on the outside. All right, I should mention that. So I'm saying you got charge Q in here, right? And charge minus Q on the, oh man, come on, marker? It's still wet or something? What's up? Anyway, so minus Q over here and Q in there. And we worked it out. We got a natural log involved here. And what we had was minus Q over 2 pi epsilon naught L times the natural log of R1 minus the natural log of R2, which works out to Q over 2 pi epsilon naught L times the log of R2 divided by R1, right? Which, let's put it all together. So what we have is charge divided by the change in voltage from the, inside to the outside conductor here. What's it equal to? It's equal to the natural log of the ratio of the radii. Oh man, I can't do math. It's not a good sign. It's fine. Give me a second here. I'll clean it up. Well, you guys can solve. Do the algebra, right? Solve for Q over the difference in the voltage. So I'm just solving. I'm bringing this over to here, which means that I should have the 2 pi epsilon naught L in the numerator. And then I believe I will divide by the log of the ratio of the radii. Right? Lo and behold, we have the ratio of the charge to the voltage, and this is therefore the capacitance. So here we go. This is the formula for the capacitance for a cylindrical capacitor like this. Again, this is unavoidable. If you have coaxial cable, for instance, right? A coaxial cable is exactly this. It's got an outer-outside braid of wire and an inside braid of wire, and there's something keeping those separate. It's not air, right? I'm assuming an air gap at the moment. We'll get past air gap here in just a second. Real coaxial cable doesn't have an air gap, right? It's got some sort of insulator that goes between the inner conductor and the outer clad, right? And so per unit meter, there's a certain capacitance, and that capacitance follows this. If you know the radius of the inside conductor of the coaxial cable and the radius of the outside conductor of the coaxial cable, this, if it was made of air, would give you the formula for the capacitance per unit meter of a coaxial cable, all right? Which matters in terms of like design. If you're, sending coaxial cable to set up an antenna and things, the capacitance will matter in the design of such a thing. Now, now here's one that has less to do with design. This is more of just a kind of a passing curiosity, I would say, which is the spherical capacitor. So, I keep talking about metals, but the truth is you could even talk about capacitance for just two surfaces and two charged surfaces and something between them. You could also talk about the capacitance of that. it wasn't actually necessary that the charges, that the plates, quote unquote, of the capacitor actually are defined by metal. They don't have to be. The plates could be wood, and you could still talk about capacitance of a parallel plate capacitor where you had like wood here and here. You could do that. It'd be weird, but you could. All right, let me get to it. So the other example I had in mind was a spherical capacitor. So here, I'll draw it two-dimensionally, but where are we? Example 4. So for a spherical capacitor, you have inside and you've got outside, right? Say radius, well, let me stick with my notation in the notes. R1 for the inside radius, R2 for the outside radius. There are some hideous typos on page 57 of my notes. I have E is equal to Q over 4 pi epsilon naught R in the radial direction. So the deal is here, guys, we're putting Q on the inside sphere, and we're putting minus Q on the outside sphere, all right? So anybody care to make a correction? To that formula? So this is for R1, big R1, less than R, less than big R2. Anybody care to correct this formula? Hideous formula. I thought this class had potential.
It's supposed to be 2.
What's that, R squared? Okay, yeah, there we go. Yes. And then I have an equally insidious error concerning the voltage. Because I soon after this say that, I'm like, okay, well, this should be minus, so this is, of course, radially outward, right? And I'm like, okay, so, well, E should be equal to minus dV dr if I'm just thinking about the magnitude of E, right? And I mean, I don't disagree with that. That's true. That's the definition of voltage as it regards a spherically symmetric electric field. Sure, granted. But somehow, I then managed to say that the voltage then is Q over 4 pi epsilon naught R squared, which is so very, very wrong. What should that be? Yeah, just not squared, right? Not squared, just that. And technically speaking, plus a constant, right? So, I mean, we could add a constant, whatever you want to call it, V naught, constant. I think I just called it C in the notes. I'm going to call it V naught here for the sake of discussion. Great. So now that we've fixed the hideous mistakes in the notes, yep.
So why can you say that if the field needs to be the gradient or the negative gradient of the voltage?
Oh, because the gradient in spherical coordinates has 3 pieces, the radial piece and then the piece which is in the other 2 angular directions. But because it has a spherical symmetry, the gradient is straight up just part of the gradient, right, is literally like R hat, partial V, partial R. And then there's like another 2 terms stuff. And these 2 terms over here involve partial derivatives with respect to the angular coordinates. But by the spherical symmetry, we know that those have to be 0. And
basically, you're saying so long as the electric field is normal, we don't have to worry about all the gradient shenanigans. We can just work in a one-dimensional.
Right. So for a spherically symmetric field, it's essentially a one-dimensional problem. The gradient just boils down to
cylinders as well, wouldn't it? As long as we were considering it head-on to the cylinder.
Yeah, as long as we're talking about the direction that's radially out from the cylinder.
Gotcha.
So yeah, and I usually, you know, if I'm disciplined, I would use S for the cylindrical radius. In physics notation, usually like the better notation is this: S is the square root of x squared plus y squared. Whereas in physics, R is the square root of x squared plus y squared plus z squared. Now, I know this is not the typical math notation, but it's nice to have a distinction between the cylindrical radius versus the spherical radius. So a field with cylindrical symmetry looks something like this. Electric field equals lambda over 2 pi epsilon naught s hat. So that to distinguish between the Coulomb field, which looks like, for instance, so the spherical, the radially outward spherical field versus the radially outward cylindrical field. They're both radially outward, but one's a spherical radius and the other is a cylindrical radius, right? They're geometrically quite different in 3 dimensions, right? Like the spherical is like a hedgehog. It goes out in all different directions all at once, whereas the cylindrical just outward from a wire, So, but okay, I'm digressing. Let's get back to this example. So what is the change in voltage from, say, B to A? Here, VB minus VA. So the V naught doesn't matter, right? It cancels. It cancels out. And so we just get Q over 4 pi epsilon naught, 1 over R1 minus 1 over R2. Lo and behold, we got ourselves a Q over VB minus VA is equal to, well, if I can do the math, it's debatable, 4 pi epsilon naught divided by the difference of the reciprocals, I think. Yeah. So there you go. That's the capacitance for a spherical capacitor. And I think there's a discussion in your book to prove that the capacitance, so if you think of the Earth, its atmosphere, something like you've got the surface of the Earth and then you've got maybe the troposphere or something like that. You could think of that as kind of like an arena to calculate spherical capacitance. And I think the book has arguments that work it out to be like a farad. So at least the previous version of the book does, because I've got a comment in my notes here. So I think, well, Survey. Are we using Survey? We're not using Survey. Never mind. So I'm sorry. There's another book out there. Some other book. Because we're using Young and Freeman. I don't think that's the same book. Okay, so again, I'm assuming that there is an air gap. So that begs the question, why do you keep talking about that? And what's the deal with air versus other things, right? So I have some figures to share with you, and I think I'll project this because they're just numbers, and it's better for me to let the projector do the work here. Oi. So just to let you know where we're going, I'm like a day ahead, which is awesome. That doesn't always happen, but yay, woohoo! And so my plan for today was just to share with you this basic definition of capacitance, how we can calculate the capacitance for a physical capacitor, all right, with a certain geometry. So it just basically boils down to, suppose that you have, charge on two plates, and work out what the necessary ratio of the charge to the voltage is in that situation. That ratio defines the capacitance, and it is something which is typically independent of time and a consequence of the particular geometry that's in play for your capacitor, and that's just all there is to it. For a parallel plate capacitor, it's super nice, pretty easy to understand. For a cylindrical capacitor, well, I've showed you the formula, so now you know it. For a spherical capacitor, I've derived the formula, so now you know it. So if I was to ask a question about those, you'd have a chance. And of course, generically speaking, somebody could come and tell you a certain charge requires a certain voltage. What's the capacitance? And what would you do? You would take the ratio of the charge to the voltage, and that would tell you the capacitance, and simple as that. So, but actual physical capacitors are not typically made with air, right? Come on. So I have made the assumption that the electric field is spreading out through, let me try to make it bigger here. Well, okay, let me try to open it up separately. This never goes well. It's just bugging me. Is there a full screen thing here that I'm missing? Am I just an idiot? Is there a full screen here? Fit the page, but that doesn't that doesn't help. What's that? Do what?
F11.
F11? FN11?
I think just F11. Not F11.
Oops. Well, that did something.
I could be wrong.
Oh, that makes my computer sleep.
Let's do FN.
It's Alt F4.
Just Alt F4. Oh, wait a minute. I'm not. Hold on a second. Ah, you guys are right. Cool, cool, cool. But this still got this pesky.
Hamburger bar at the top.
The hamburger.
Yeah.
Ah. Oh, thank you. You guys are geniuses. There was a student who showed me about 3 or 4 years ago, like the Shift Alt S thing for, for taking screenshots. This thing. Whatever it is. Yay. That's been life-changing. So anyway, I digress. Now, if I can just remember what you guys just told me, then I could use this for future lectures, yeah? That'd be nice. Okay, so here's the deal. If you have an electric field which isn't spreading through free space, but it's actually spreading through air, it actually spreads out differently than in the vacuum. Now, it turns out that the distinction between, so the ratio, so here's how it works. You can define kappa for your medium, and it's the ratio of the permittivity of the medium versus the permittivity of free space. So for the vacuum, the kappa is 1 because the vacuum is the vacuum, so it is epsilon naught. Air, it turns out the kappa for air is 1.00054. So for all intents and purposes, air gap is pretty much the same as vacuum, which is why I wasn't lying to you much up to this point in the course. That said, every example I've done where we had an electric field going through an insulator with uniform charge, in some sense has been not good. Technically speaking, I should make all of those modified. I should modify the permittivity inside the insulator to be epsilon. The only way that actually makes sense is if the material is what's called a linear dielectric. A linear dielectric is a material where the electric field propagates as if it were empty space. Now, there are other materials which are more exotic where the electric field inside those materials does not propagate like it's empty space. It does something more quirky that's a consequence of the particular crystalline structure and the electronic details of the solid. That's not something we'd ever talk about in a course here. As far as I know. Do we have a course in solid state physics? No. I don't think we do. So we should. We should. Maybe we will someday, but demand it. So that's not my thing. But anyway, other materials like diamond has a ratio of the permittivity of diamond to the permittivity of free space about 5.7. So the permittivity of diamond is way higher than air. The permittivity of water, 80.1. The permittivity of ice, 99. So ice and water electrically quite different. Well, a little bit different. And this thing, I don't know what this is. Any of you chemists, can you tell me? Is potassium. It's canabadobodo. What? What do you say? Well, whatever that is, it's got a permittivity of like 34,000 times that of the vacuum. So that would make pretty nice capacitors if you could find some of that stuff, right? So this is taken from Griffith's Electromagnetism, which is a wonderful book if you want to understand next level electromagnetism. It's really a great book. Here's a picture of basically what's going on. I'm not quite there yet, but the net effect of it is if you have something between the plates instead of just free space, instead of doing epsilon naught, you do epsilon. So that's the difference. Basically, Gauss's law gets modified. Instead of dividing by epsilon naught, you divide by epsilon. And so everywhere we had an epsilon naught, we replace with an epsilon to account for the way the electric field goes in something other than air. And typically that's going to make the capacitance bigger. See, because all those kappas we just looked at, all the epsilons we just looked at, they're larger than the vacuum, right? So here's basically the reason for that is something like this. The electric field lines, if they go between plates in the vacuum, they just go, right? But if they've got to go through a material which is actually has a polarization, that means that you've got a regular crystalline structure of your solid, and it's arranged such that the actual molecular dipoles are arranged like such, then the net effect of it is that these line up with the E field, and you end up with like less charge here and there overall, so you have a lower E field effectively. That's one way to understand it. I'm sure that's a lie in some regard. It's actually a complicated business why this actually happens, but that's not part of this course, so don't worry. But this is the first order explanation for why you can just replace epsilon naught with epsilon for a linear dielectric. Of course, that does lead to other questions and nice homework problems in terms of dielectric breakdown, right? So what you guys know what dielectric breakdown is? As long as we're talking about dielectrics, let's break it down. So this is the maximum voltage that you can have per meter without the electrical energy just vaporizing what's between there and just, shock, right? So if you put more than 1,000,000 volts per meter on glass, you'll turn it, no, it's already glass. It'll become molten. I don't know. It's going to destroy.
It'll vaporize and destroy anything that hits
It will vaporize, and you don't want to be close to it when it happens. Polystyrene, 2 million. Wait a minute. Oh, that's 10 million, isn't it? 10 million volts per meter. That's a lot. 20 million volts per meter. Air, dry air, about 3 million volts per meter. So if you just have, if you got, two people holding, wires, and one is, 3 million volts different than the other, as long as they don't get closer than a meter, it shouldn't really be a problem. Unless the air is too humid, and then it could be a problem. But anyway. And that's pretty much what I wanted to talk to you guys about today. So we'll talk about energy stored in capacitor next time probably. But what's the question? For what the what? Breakdown? Oh, it just arcs. It just breaks. It just burns the dielectric up. So the capacitor's kaput. And gone, dead. So next time we'll start into circuits. Thanks, guys.